Invented in the 19th century, fuses are designed to blow whenever there's a power overload. This stops the flow of electricity and prevents a wiring fire. We may never see fuses in action, but they're constantly working to protect us wherever electrical current flows. Choosing the right fuse depends on the amount of current. To make a high-voltage fuse for use in electrical substations, this machine cuts notches into a long silver strip which will serve as the fuse's element. The notches will help control the way the fuse blows. Bits of soft metal are melted onto the strip. These will be the points where the fuse blows. One end of the silver element is welded to the top of a ceramic core, and the element is wound around it. Workers slide the element core into the fuse casing and bend back metal tabs. Then, using a soldering technique called brazing, they seal everything together. They take a brass washer and wind ignition wire around it. They're assembling the striker pin, the device that indicates a blown fuse and shuts down the power. The striker pin is fitted to the washer, and with the wire protruding, it's placed into a holding device. Explosive powder is added to each striker pin. Then the bottom of the pin is plugged with a rubber stopper. Next, the striker pin is pressed into a brass capsule. This will contain the mini explosion that pushes out the pin when the fuse is blown. This test run shows how it all happens. The pin's ignition wire is wrapped around an electrical post. Workers clamp down the pin and position the pendulum that swings to indicate the amount of force with which the pin fires. A jolt of power detonates the explosive. This causes the pin to protrude, signifying a blown fuse. Now, a metal eyelet slides onto the striker pin's ignition wire, and then a wire coil is attached to it, completing the striker pin's ignition system. A snare pulls the whole assembly into the fuse. The end of the coil is tied to the fuse's cap, and an outer cap is press-fitted over the inner one. Next, the fuse is filled with sand. This sand will absorb energy from the element when the fuse blows. Automated rods tap the fuses to compact the sand inside. Next, an outer cap is lubricated. And it's pressed onto the other end of the fuse. This machine spins grooves onto the cap, pinching it tightly to the fuse casing. A current is run through each one of these fuses, checking the voltage to confirm that they're in good working order. Sealant is then pumped around the cap's rims to make them completely airtight. Finally, the safety information is affixed to the fuse. And some electrical specifications are stamped onto the caps. Now, these fuses are ready to go with the electrical flow and blow at the first sign of trouble. If you have any comments about the show, or if you'd like to suggest topics...
Tires for construction and mining equipment are truly giant-sized. They can be twice the height of a human being and weigh thousands of pounds. These giant tires also come with a hefty price tag. Just one can cost more than an average family sedan. Giant tires are made to carry heavy loads in conditions that are seriously off-road, like mining and construction sites. To make giant tires, they feed rubber into a powerful mixer. They add sulfur and antioxidants to boost the rubber's durability, as well as recycle pieces of used tires. At the top of the mixer, they add carbon black in measured amounts. It's an oil byproduct that helps bind everything together. The mixing generates heat, which softens the rubber, making it doughy. The rubber dough then falls between rollers that squeeze it into a sheet. The process is called milling. They slice the sheeted rubber and feed it back into the machine several times. This repeated milling essentially kneads the rubber to give it the right consistency. Once the rubber has been sufficiently processed, they feed it to a conveyor. A wheel rolls over the rubber to impress the date and identification number onto it. The rubber then winds through a tank of soapy water. As it exits, it falls over hangers that move it through a dryer. A soapy residue remains, keeping the layers from sticking together as they await more processing. They write the ID number on a sample of the rubber and tag the production run with the same number. This signifies that testing is underway. They tuck the test sample in a canister and send it up a chute to the lab. Once it's confirmed the rubber has the right characteristics, it's ready to be made into the various components of a giant tire. At the next station, dozens of steel cords unwind into a machine. Each cord is made of numerous steel threads, and each thread is brass-plated. These steel cords will be used to fortify the processed rubber. The cords enter a machine called an extruder. It grinds and heats some of the processed rubber and then forces it around the steel cords to encase them. The result is what's known as steel-belted rubber. They cut several of the steel-belted strips on an angle and fuse them together. This exposes steel cord around the edges, so hot rollers seal them with rubber. The steel-belted rubber will make the tires more resistant to punctures. But they make the tire's basic structure from rubber-coated nylon cord. They cut the nylon rubber ply to a specific length. Workers then piece several of these sheets together to form a loop. The pieces adhere because uncured rubber is naturally tacky. And a machine rolls the loop to the correct size. They layer more of the nylon rubber ply in a crisscross fashion to add strength. The machine that helps size the loop also applies a thin layer of ordinary rubber between each crisscrossed layer. This thickens the rubber loop. The finished loop is called the band. It's the skeleton of the giant tire. They hoist it onto a cart and move it to the next station. Stay tuned as they shape and inflate this band of rubber to turn it into a giant tire. This machine is about to stretch the big band of rubber like an elastic. The machine pivots, and its many rollers expand and turn to transfer the band to a spinning drum. The machine pumps air around the protruding rollers to make the transfer easier, while the drum turns at a constant speed to aid the process. Once the transfer is complete, the rollers retract and the air escapes. This causes the rubber to shrink to the drum and take its shape. They fold the overlap into the center of the drum. The giant rubber band now has the basic contour of a tire. Next, another machine coats numerous steel wires with rubber, creating strips of rubberized steel. This will be used to make the bead, the part of the tire that sits on the wheel rim. They wind the rubberized steel around a metal wheel up to 20 times to form the bead. They remove the bead and inspect it. Then they pack a thick layer of rubber onto it, so it will be easier to shape to the tire. Using a special applicator wheel, they push the bead against the lip of the rubber tire shape. The bead adheres, but it needs to be more solidly attached. A spinning disc forces the bead more firmly to the rubber tire shape. Then, the tire assembler folds back the extra rubber from the tire and wraps it around the bead using sheer physical strength. They install 2 or 3 beads on each side of the tire. The multi-roller device takes over from the assembler and folds back extra rubber to lock the beads in place. Next, the tire turns as they wind steel-belted rubber around it, followed by a continuous strip of ordinary rubber. That strip builds up contours for tread. The assembler then wraps a thick piece of ordinary rubber around the outer edge. This is the tire's sidewall. The spinning disc device presses the sidewall to the tire. This tire is now ready to move on. Here, a huge rubber bladder inflates and deflates as they spray it with a non-stick coating. This bladder will act as the inner part of a mold. They lift the tire onto the deflated bladder. They then pump steam into it, expanding the tire. A metal mold with a tread pattern engraved in it closes around the swelling tire. The tire cooks in this mold for up to 18 hours, causing the rubber to cure. The giant tire pops out of the mold with tread. The brand name and identification numbers have all been molded into the rubber. After cooling, an inspection team examines the giant tire inside and out. And once it gets the okay, it's ready to roll. And with all that deep tread, each giant tire is guaranteed to make a big impression on the job site. It's hard to beat the glitter and glow of glass Christmas ornaments. For many people, the Christmas tree just wouldn't be the same without them. They were invented in the 19th century by a German glassmaker who decided to improvise because he couldn't afford to decorate his tree with the usual nuts and candy. They're Christmas eye candy. Today's glass ornaments are a visual treat. To make some of the ornaments, they start with a sketch and make a plaster model of it. They use it to create a two-part metal mold. They take a glass cylinder and fire its wider end so it softens. The glass maker blows into the pipe end to stretch the supple glass into the basic shape of a bauble ornament. Other glass tubes are more bulbous at the center, and that's the section that's fired, as the glass maker blows it into a more elongated bubble. He places that bubble in the mold and blows extra hard. The glass expands into its crevices and takes its shape, a snowman. He burns off one of the blowpipe ends and then aims the torch at the snowman's nose to pull it out. A quick cool down could shatter this ornament, so he gradually lowers its temperature with a less intense flame. Blowing and molding glass figurines is quick work. The glass maker has just a few seconds to complete the job before the glass becomes too cool and stiff to shape. The ornaments now head down the line to get some shine. This will be an inside job. The glass maker pours silvering solution into the baubles through the stem. She then dips the bauble in warm water. This activates the silvering chemicals, and shaking the ornament accelerates this process. She swirls the silvering liquid around to completely coat the inside of the ornament. A final dip gives this bauble a mirror finish from the inside out. She empties the silvering solution into another tank for recycling. They also use this technique on the figurines, like the snowman. A quick shake gives this guy an inner beauty. Next, they submerge the glass ornament in lacquer to give it some color. The mirror finish inside shines through the lacquer. Now the snowman ornament gets an artist's touch. She airbrushes white lacquer onto the figurine for a frosty finish. It makes the snowman look more like Old Frosty. The artist paints some of the details by hand, like the trim on the hat and robe of the Santa ornament. This gives it more visual depth. Once the paint dries, she brushes glue onto sections where she wants glitter dust to stick. The glue dries quickly, so the artist applies more. When it comes to Christmas sparkle, you just can't get enough. Next, she makes an incision in the stem and snaps it off. A metal cap fits on the ornament stub. Time to pack up these fragile beauties very carefully. They put them in boxes that cradle each one individually to ensure they arrive safely. Now, these glass ornaments are ready to go out on a limb to add beauty to the holidays. Gliding involves flying unpowered aircraft. Though some models are fitted with a small engine and propeller, so they have the power to launch into the air on their own. No matter what the model, the sport of gliding is all about the joy of using the forces of the atmosphere to fly higher, faster, and longer. Gliders, like this model version, have three main parts: wings, fuselage, and tail. Workers build each part of the glider in two pieces, using resin and steel molds. They begin with the fuselage mold. They lay down strips of Kevlar, a strong heat-resistant material. Then they apply epoxy resin to the Kevlar fiber to reinforce it. They leave the epoxy to dry, and the next day apply strips of carbon fiber to reinforce the fuselage. The direction in which workers lay down the fiber layers is key. In flight, gliders are subject to strong forces that can bend and twist the structure. They must be sturdy, yet as light as possible. The glider's tail boom gets the same treatment, except where the antenna will go, as radio signals don't penetrate the carbon fiber very well. Workers apply a thin coat of white gel paint to the 30-foot wing mold. Gliders are always white, so they don't absorb the sun's rays and overheat. They roll a sheet of carbon fiber over the painted mold. Then, the entire assembly team skillfully applies an even coat of resin. They've got to be quick. The resin cures in just 30 minutes. They add a final layer of carbon fiber to strengthen a portion of the wing that's subject to strong wind currents. After laying a white fleece over the layers of carbon fiber, they seal it between two sheets of plastic. A vacuum compresses the layers, which draws excess resin to the surface, where workers can remove it. The two wing parts are glued together using the same epoxy resin that bonds and seals the carbon fibers. Mixing in some cotton flakes helps thicken the resin, which they apply to the main spar, the wing's backbone, then to the front, back, and center portions. Using a crane, workers carefully fit the two wing molds together. The mold's weight forces out any excess glue. They tightly clamp the two molds together and leave them to harden overnight in an oven heated to 140 degrees Fahrenheit. The next day, there's a loud pop when workers separate the two molds. They carry the completed wing structure, which weighs only 132 pounds, over to another area to trim the resin overflow and sand down the seams. Using a diamond tip cutter, they cut the wing in two for transport, revealing its inner structure. Then they make sure they can easily put it back together before going on to the paint shop, where they reassemble it. Workers scan the surface and mark the areas they will sand by hand. They mount the glider's fuselage on a rotating stand so they can easily access the entire surface. They sand it and then polish it to a mirror finish. As workers assemble the glider, they inspect every system. They check the engine command that lowers the glider's launch propeller and retracts it into the fuselage. The landing gear must lower and retract smoothly out of the glider's undercarriage. Now they reassemble the wings. They check the air brake located in the wing. And finally, they install the canopy. The glider is complete. Sturdy yet light, this mid-size model can reach speeds of nearly 186 miles per hour thanks to its sleek design.
Because the world is round, flat maps don't give us the full picture. A globe is the most accurate representation of the Earth. It depicts countries in true spatial relation to one another and better defines latitude and longitude lines. the globe factory, production revolves around world events. As war and political upheaval redraw boundaries, these spherical maps have to be constantly revised. Globe construction begins with a big roll of cardboard. A machine pulls it under a roller that coats it with glue. A knife then slices the cardboard into smaller pieces, which will serve as liners for the maps. One more coat of glue, and then the liners are attached to the back of maps. Heated rollers press them together, completing the seal. Each map represents a hemisphere. A powerful press now cuts the maps into a pinwheel shape. Each map must be carefully positioned in the cutting press. After all, one false move and a whole country could end up on the factory floor. It takes 2 punch cuts to do the job. Then the excess paper is pulled away, leaving behind a map divided into 12 spoke-like sections. Here's a top view of that cutting press. It acts like a giant fist to punch out pinwheels. And now it's time to shape the world. Workers place a map cutout and a liner into a mold. It rises into a heated cavity that presses the paper into a bowl-like shape. One hemisphere down, one more to go. The southern hemisphere is created using the same type of mold. Molds also emboss each map to represent the peaks and valleys on the Earth's surface. Here's an inside look. The raised and indented sections of the molds allow people to see and feel variations in the world's topography, both above ground and underwater. With the hemispheres complete, it's time to go global. The northern hemisphere goes for a spin while a razor blade trims the edges. Then the lower hemisphere takes its turn while a nozzle beads hot glue along the inside. This stiff cardboard ring adheres to the globe and gives it some reinforcement along the equator. Glue is applied to the northern hemisphere, and it is fitted over the ridged edge of the southern one. The two halves are precisely aligned. Then tape is attached over the seam. This both disguises the seam and marks the equator. Next, each globe is mounted on a pedestal that's attached to a metal arc called a meridian. Suction to the top of the globe, the meridian will allow the Earth to revolve. From fragments of paper and glue, a whole new world's been created in just a couple of hours. Globes tell us where we are and help us figure out where we're going. They come in many different languages, and because they help us get our bearings, you could say they make the world a better place.